know what the main point here is? What is the most important? What are the most important? Okay, maybe. What is the most important word, or what are the most important words? Yeah. What is the most important word in this whole collection? Oh, yes. I have to specify that this is not just a few numbers or one number, but all numbers. That makes all the difference. So you have, this is sort of automatic. You must do it. No matter how much you think people understand you, well, you can't take that chance. Now, why I lump the two together? Because this thing about substitution, the reason you begin to think that that's important, that's almost a big idea that we should emphasize, is the statement that we have in the school culture, school mathematics culture, we have lost track of what symbols are for. And therefore, when you see a symbol, you think it's something special. And then, for example, instead of talking like this, let me give you an idea. X be a number. Number. So that 3/4 of X times Y. If Y is 58, then X is 3/4 of 58. Oh, sorry, twice one. If I say this. Now, of course, I purposely say it this way, but in fact, this is what you would call a substitution, because what it says is what? 3/4 of X is Y, and then your Y is 58, right? Then you say, I am substituting Y with 58 into here. Right? That's what you would say. I'm doing a substitution. Of course I'm doing that thing. I can't. Look at this. Forget about the symbols. I have something. Twice of it is 58. Now, on the other hand, I also know that that is equal to 3/4 of X. What do you think 3/4 of X is equal to? Do you need a substitution? What does equality mean to you? Equality of numbers means what? They are the same number. They're the same point on the number line. So this is a basic common understanding about the English language. What I'm saying is that you did something. On the one hand, it's 3/4 of X. On the other hand, it's twice 58. So what do you think? So I'm saying 3/4 of X is twice 58. That's what I said. No, I forgot. Anyway, I got it wrong. Oh, yeah. Sorry, no wonder. Yeah, sorry, I'm sorry. No wonder. Look at me funny. Yeah, that's what I said, right? 3/4 of the X is a number. It's try something else. And that something else is actually 58. So, what do you think I'm saying? That's exactly what I'm saying. I don't need any substitutions. That's exactly what I'm saying. Now, do I get this across? Do I get this idea? Am I saying something that you don't understand? Do you think I need some thinking process for this to be true? this understandable? That's what I meant. Yes or no? Huh?
Yes or no?
Yeah. Yes. What I'm saying. Understandable. True or no? I'm off. Oh, so you all understood. Oh, thank you for that. I mean, this is a very basic message that symbols are at your command. Therefore, you should not think of it as something far away and distant. And so every time you move it, you have to call on some idea to say, I just use that idea in order I can make sense of what's written there. So if you used to look at symbols, and each time you know exactly what the symbol is, no guesswork, then you treat it as everyday language, which is what it should be. Mathematics is everyday language. More precise, yes, but it's dependent on the English language. It's no different. So that's why I want to lump it together. Basically, what you have to do is to take a different attitude about symbols. If you find things in the book that abuse this cardinal rule about all symbols must be clearly specified as to what they are, and therefore you find that the book not readable, the fault is not with you. The fault is with the book. I hope you don't find things like that in the book in front of you, because in each case, the symbol is always clearly specified what it is. And therefore, you treat it as everyday language. A symbol only does abbreviation for you. No one says, JFK, USA all the way now. You see? JFK, does anyone even know this phrase? JFK, USA all the way. That's back in 1960 when he was running for the president. There's full of symbols there, agree? Yeah. Was JFK, not J, not F, not K, but a person. You know that, right? You don't look at this and say, my God, you have a J, you have a F, you have a K, what do I do with it? You don't say that. You say that is a person. You understood. Same thing here. You have a number X. What is it? X is a number, so you say 3/4 of some number. It's not some symbol that you cannot lift up, you cannot use, cannot move. It's just like any other number. 5, 22, 82.5, the same. So in terms of everyday language, there's no extra idea needed to make sense of this and to conclude something like this. It's just standard English.
But that's not the only idea of substitution. You could also call 58 5 tens and an 8, or 49 plus 9. You can use any version of 58.
Absolutely. Absolutely. When that comes by, I have never used anything like that, you see. Yes. That comment was where?
It was for the exponential notation where you replaced 100 with 10 tens and then you replaced 1,000 with 3 copies of 10.
Oh, but that's a different context, right? So let me see. This one.
I think so, yes.
I told you, right? This is a theorem.
Yeah, it wasn't like one. It was right, it was
Right? That's what I wrote. And I said, why did I write this? Because you got tired and I got tired of saying 10 is equal to 1 with 1 0.
Why would it not be?
10 squared is equal to 1 with 2 zeros. 10 cubed is 1 with 3. We got tired of that. We say, let's find a way to say it once and for all. Let's just standard language and say, like JFK, you don't want to say John Fitzgerald Kennedy. You get sick of it. You say JFK. Well, you say, nothing extraordinary about that at all. USA, for example. Why do you say USA? Well, because you got sick of saying so many things, so many syllables. So this is the same thing. I got sick of writing too many times and not quite expressing myself. So I said like this, and it's understood that here it is, no matter what n is, it's going to be true. Again, there's no substitution involved.
But that comment was on something different.
I see. So you have an explicit example, then I will explain that or do something. But in general context of substitution being important, that's not in our present context. I don't think I've ever used anything about substitution, this substitution, that. It doesn't come up. Okay, so if you have questions about this statement, we'd better talk to each other after, right? But the general idea of your understanding of how symbols are used, that is of critical importance in teaching of mathematics at all levels. Okay? Okay.
All right.
What's the next one?
Why are we using 6x10 rather than 6.10 or 6 beginning parentheses 10 end parentheses?
Well,
That's the
like
dominant.
saying, why do we use this? Why do we use this? And why do we use that? It's just exactly the same thing. It's a symbol that you can use that's quite clear. For little kids, you say instead of this, write the dot. See, you people don't teach elementary school, so you don't understand. That's why you want to trust little kids to do this.
I do both. Yeah, I teach both in elementary, using the X first and then changing to the dot.
You can do it, but is there a pressing need?
It depends. Sometimes, yes, but would be, especially for ending up with X's in there, you know.
You're actually going to the ask.
Well, you see, the context of using, the context of doing arithmetic with these explicit symbols is that you don't introduce letters.
Right.
The minute you introduce letters, then of course you need to replace it for the reason I just gave, that you don't want to confuse it. So the X is used because in beginning arithmetic, first, second, third grade, you don't use X. And therefore, this is by far the better symbol to indicate to people I'm multiplying. That's all. Nothing unusual. Right. In any case, well, I mean, to be honest, no matter what kind of mathematics you do, if you use just explicit numbers, 58 times 27. If I were you, if I just use cross, it's far clearer. Because again, you use a dot, you have the mercy of the reader. I mean, it's open for misreading and everything. Yeah. So that's all. The use of symbols is dictated by one thing, or two things rather: brevity and clarity. Nothing else matters. Same thing for also. Anytime you use a symbol, ask yourself: does it make it clearer? Does it make it simpler? Okay.
Let's go.
That's it?
No,
Oh.
remember we have a whole bunch of questions. Next question. If we teach students about 4 operations, at what point would it make sense to explain that there are only 2 operations and their inverse?
Well, it's not so much at what point it makes sense. You have to learn enough mathematics to be able to understand what's going on. So there's no way you can understand why division is less multiplication until you have done fractions correct. And that means you have to do fraction division correct. And that comes only at least in grade 6. So, no, just simple division doesn't count.
We divide our fractions in current fifth, in common core, it would go on, but right now, it's a little different.
In grade 5, you can mention division. You can do a few monkey around with it a little bit. But nobody, I don't think anyone has any sense to do full-fledged division of fractions in fifth grade. Does not happen. Check. Go check right away.
No, yeah, you're right.
Of course. I read a lot of these things.
I think this is the last one. Okay. Why not teach time?
Oh yeah, sorry, let me mention the subtraction. You don't learn about subtraction as being addition until you have done rational numbers correctly again. So that most likely comes in grade 7. Grade 6 is very simple. Most likely 7 and 8. Most likely. So it's not a matter of saying what is the right time to jump in and do it, but rather as your mathematical development led you to the point where you can understand it. That's the issue.
Okay, last one. Why not teach time? Why not teach 12 times tables? There's value in learning the 12s for inches, feet, yards, etc., and hours in a day. So why not teach it in 3rd grade?
Okay, now I made some comment about that, and I don't want that to be misunderstood. Whatever you learn, and you think it helps you, you should learn it. You can learn, you can, I have friends, my colleagues, sometimes they know the squares of all integers between 1 and 100. It's wonderful. These are professional number theorists, and they use it every day. Well, now, what I was discussing was a matter of what the state standards are like, or what kind of textbook, what things are said in the textbooks. This is a matter of making all the students do certain things. That's a very risky proposition. Don't do it unless you are you have firm evidence that what you are recommending, what you're making them do, really is conducive, is helpful to student learning and to student achievement. From that point of view, it's totally sensible to require, that's the operative word, you require all students memorize everything between 1 and 12. Because what's the need? Mathematically, there's no need. You solve this model, right? All you need is single digit. Therefore, you say, I like my students to learn it, and in a small classroom, you're the boss. If your students don't rebel, you can do basically pretty much what you want. But in terms of writing a textbook, you're in trouble, because that would be open to challenge. Why do you require all students memorize the multiplication table from 1 to 12? There is no mathematical justification, and you better think twice. So I hope this what I said is understood in that context of state policy or uniform requirements for all students. That's a very risky proposition. So I hope that's understood, right? Did I leave something that you have questions about? Okay, so let's go back to this, to the burning issue. Okay, so the review, right? So we're talking about division. So it's understood that when you write this down, is already known that this is a multiple of n. Multiple, you know what multiple means, right? It's some whole number times it. So then, I'm trying to tell you that, oh, by the way, that number, of course, you all know what this number is called, right? What's that called? K. What's that number called? The quotient of the division, right? That's the quotient. Okay, I should have been more clear, right? So this is the quotient. And all I'm saying is that this quotient has two distinctly different interpretations. One is called the partitive interpretation. It says the quotient is exactly the number of objects if you divide the m objects into n equal groups. The n, the divisor, dictates, and that's why it's called partitive, dictates how you partition the group of n objects into how many equal groups? Well, that's what n comes in. You divide m object into n equal groups. Now, and then look closely to each group and say how many things are in there, and then that's what the quotient k is. The measurement interpretation is opposite. By the way, you know why it's called a measurement interpretation? It's exactly measuring, right? Think of, so we were talking of 18 and 6. So suppose you have a piece of wood, 18 feet. You want to make tables of length 6. Just trust me. 6. You say, how many tables can I make? You measure. 6, 6, 6. Conclusion, you can make 3 tables. That's why it's called the measurement interpretation. Now, there are other names for that, but I like this better. Now, that's a completely different way to look at the number of the quotient k. Off the bat, they look not related. Really. Right? So why are they the same? Well, that is because 18, is 3 times 6, right? You know that. Therefore, is equal to 6 plus 6 plus 6. What does it mean? So addition, no matter how you look at it, is combining things. Well, in terms of the number line, that means what? You have a segment where you obtain the segment of 18 feet, let's say, by concatenating 3 segments, each of length 6 feet. So that's a clear-cut exhibition of how many 6s there are in 18. 3. That's the quotient. You know ahead of time. Yeah? So that quotient measures how many 6s there are. On the other hand, but multiplication is commutative. Therefore, this is 6 times 3, and as such, it becomes 3 plus 3 plus 3 plus 3 plus 3. Is that enough? Sorry, one more. What does it say? Because this is 6, see? Ahead of time, you know there are 6 groups here. You are dividing 18 into 6 equal groups. There's nothing more equal than that. 3, 3, 3, 3, 3, 3, 3, right? And now you ask, how big is each group? That's the question.
Oh, which one is which? Isn't the first one the measurement and the second
It
one
is.
partitive?
It is.
First one measurement,
Yes.
second one partitive.
Yes.
Thank you.
Yes. Right? I have 3 groups of 6s. That's what this is. I'm measuring 18 by 6. How many are there? 6, 6, 6. But this is dividing 18 into 6 equal groups. Ahead of time, you don't know how many are in each group. You don't know. turns out it's the 6 feet. The 6 feet. So now, look, if you do this to your kids, this would be, wait, 3? Probably. Yeah, end of grade 3, am I right? Someone should, beginning of grade 4, it's somewhere there. Changes from state to state. If you do that and tell them you're using the commutative law, you don't have to say it, but you just show them because I can multiply two whole numbers, regardless of order. People, I mean, young kids would form a much better opinion of all those laws: commutative, associative, distributive. And the failure of children to take those things seriously is not a reflection of anything but how they've been correctly instructed. Right here you can see, it's almost miraculous actually, when you think about it.